Yes. Now kV is what? The velocity factor or dynamic velocity factor. It is based on the mean pitch line velocity Vm. What is the mean pitch line velocity? The mean pitch line velocity is, in general formula, it is pi dn by 60. If you consider d is in millimeter, then divide by 1000, convert into meter. Just a pi dn by 60,000. That is get meter per second. Now which one you consider? Doesn't d is what? Physical diameter that I want to represent in terms of module into a number of teeth. Module into number of teeth. Now which is a weaker member is that weaker member is choose the take the formula and substitute. Then based on the Vm value, we'll go for refer the equation number 23.13482 to 23.137a. Based on the Vm value, mean pitch line velocity. If mean pitch line velocity is less than 7.5 meters per second, then we will go for use equation number 23.134a. The mean pitch line velocity between 7.5 to 12.5 meter per second, then we use another formula. Then if we have mean pitch line velocity more than 12.5 meter per second to 20 meter per second, we use another formula. Okay, that is a what? Kv is a velocity factor, dynamic velocity factor. Okay, now refer this equation in 23.134a to 23.137. Now we'll move on to the data handbook. Now as you know, the tangential tooth load from Levis equation is the equation number 23 point 23.93, right? 23.93, equation number 23.93. Now see that from Levis equation, what is the tangential tooth load? It is Ft is equal to sigma naught into B into Y T into Kv, right? Right? Next, then how to determine Kv value? Kv is depend upon the equation number 23.134a. It depend upon mean pitch line velocity pi dn by 60,000, where d is equal to m into z is substitute. 23.134a. Yeah. See the dynamic or velocity factor. Now it is visible. Please check the dynamic velocity factor. Is anyone give me response? Does anyone give me response? Please respond to my question. Does anyone give me response? Am I audible?
Yes, sir.
Visible, sir.
The screen is visible. The PDF file, data handbook.
Sir.
Yeah, in this
Yes,
dynamic or velocity factor, you can see this that we represented sometimes kV or CV. That values varies from mean pitch line velocity, how much it lies. The Vm is less than 7.5 meter per second, then we use this formula. If Vm is greater than 7.5 less than 12.5, then we go for use this equation. If Vm is greater than 12.5 less than 20 meter per second, then we'll go for use this formula. Okay, depend upon the mean pitch line velocity, we'll go for assign the formula for dynamic or velocity factor. So again, this Ft is also will get in terms of module only. Now the first tangential two-third from power equation also the FT equation will get in terms of module unknown. Second one tangential two-third from Lewis equation also when you substitute that also will get FT equation in terms of module only. Then how do you calculate module? Then we'll go for compare those equation. Compare equation, yeah, by comparing that equation, by equating the equation 23.87b and 23.93. Papa, by equating the equation 23.87b and 23.93 by trial and error method. By trial and error method, we go for calculate module. Now, how do you calculate module? See that better you go for constructed table. In the table, first trial number, first we'll go for assume the module M 4 mm, 5 mm, 6 mm like that. Now that module, the mean piston velocity also you get in terms of module. There's a pi d n by 60,000. That is d is unknown. That is m into z. Module is unknown. Then based on this Vm, we'll go for again velocity factor we have to also determine. Then from the velocity factor, when you compare the equation 23.87b and 23.93, that we will get in terms of m cube kV. That should be greater than or equal to some value we will get. Then if condition is satisfied, then you go for suitable for the suitable that, then you go for select that module. Then how do you select the module? Again you go for refer the standard module. There's a table 23.83. Page number 23.61 it is. Then by referring the table 23.3, then you go for select the standard module. Clear? Yeah, always go for select the module by considering module m is equal to 4 mm. Here it's a 4 mm itself is a suitable means then we go for choose 3 mm, 2 mm like that. Decreasing this module. Okay. By taking the table. When it's come to solve the problem, you come to know this how to take compare those two equations. Right? Once you select the module, then you go for calculate mean piston velocity, kV value, and tangential tooth load value, etc. So this is a design against static load. After once you select the module, then how do you judge whether the module is suitable for the specification is right or wrong? How do you check? Then you will go for the check the stresses induced in the gate teeth against a static load, whether it is safe or unsafe. Now on the next slide is visible. Please check for stresses.
Yes, sir.
Yeah, in check for stresses, again in that two varieties are there. How do you check? Again from the design data handbook. First, you calculate the induced stress. The induced stress is equal to sigma naught into kV induced. This is a just rearranging the equation number 23.93. Rearrange of that equation 23.93. Sigma induced is equal to sigma naught into kV induced. That is Ft by B into Y into P. Next, we go for calculate all over stress. All over stress is sigma all over is equal to sigma naught into kV all over. Sigma naught, you know that the all over static stress per weak member, kV already we calculated in the previous calculation. The substitute. What the design conditions here? Whatever the induced stress should be less than the all over stress, then we can say the design is satisfactory. Now the design is safe. Right, this is a one way we go for check. Second one is we go for calculate effective force. Effective force is nothing but ft into cs divided by kv. Cs already we use in service factor. This is a modified equation of 23.87b. Only take effective force is equal to ft by kv. Ft already we determined, kv also we know that. Substitute what will be the value you get? Effective force. Then you know that from the design data handbook again what is the beam strength of the, there is sigma naught into b into y. This is a modified equation. This by omitting the kv value, modified equation of 23.93 by neglecting kv value, the same equations you will get here. Then substitute here. Then what is the condition here? Whatever the effective the bending strength of the beam, that should be greater than the effective force. Then you can say the design is safe. Design is safe. Right, that gives a factor safety is greater than 1. The bending load should be more than the effective force of the tooth. Then design is safe. This is a way how to check the stresses induced in the gear tooth against static load is safe or unsafe. That completes what? Step number 2. In the first step number 1, identify the weaker member, whether gear or pinion is weaker. Step number 2, design against static load. In the design against static load, first you go for determine tangential tooth load from power transmission. Second one, tangential tooth load from Levy's equation. Then compare those two equations, you get the module. The third step, check for stresses. What are the induced stresses should be less than the all over stress. What are the effective force should be less than the bending stress, bending load. Then you can say the design is safe against static load. Now second step over, right? Now what is the third step means? Third step, then we go for take the dimension. Once you know the module, displacement velocity, kb value, tangential tooth load, all the things, then you go for determine the dimensions. How do you determine the dimension of the gear for both gear and pinion by referring table 23.1. And once in that, you can see the addendum, dedendum, working depth, total depth. This mainly depend upon the pressure angle. Clear? And the module, second one. And also calculate the center distance from the referring the equation 23.19. Okay, these things you have to calculate. This is the third step over. Determine the dimensions. Yes, now we'll go to the data handbook. Table number 23.1, right? 23.1. The first equations will come, next figures will come, next tabular column will come. Okay. The table number 23.1. I think it is visible. Please check. Table 23.1, gear tooth proportion. This is visible.
Yes, sir.
Visible the data handbook, table 23.1. Just give me answer.
Visible, sir.
Yes?
Yes, sir.
Yeah. In this, based on the pressure angle, so ACMA means American Gear Manufacturing Association. I think you know about in DME one, you studied codes and standards, right? In the standard AGMA means American Gear Manufacturing Association. That is AGMA standard. It is in that for 14.5 degree invalid, or 20 degree full invalid, or 20 degree stub invalid. These three, the profile invalid profile and pressure angle, we can see that. And these are the two characteristics you should take here based on what. So for example, 14.5 degree based on it you get in terms of module only. Okay, these data you should take and also take the center distance. Center distance what equation number 23 point. What's the equation number 23.19. Equation 23.1. As you know, the center distance formula is d1 plus d2 by 2, right? For a gear 23.19. But here instead of diameter given in terms of what? The number of teeth and module. Center distance A is equal to, I think is visible. Please check. A is equal to m by 2 z1 plus z2. This is center distance formula. Or m into z1 is what? d1 plus m into z2 what? d2. d1 plus d2 divided by 2. That will be the center distance. Yes, the third step over. Next, fourth step is design against dynamic load. The design against dynamic load. Again, dynamic load occur due to some inaccuracies are present In when we go for measuring the gear tools or measuring the gears, right? And what happens? The dynamic load is always greater than the tangential tooth load. The tangential tooth load is a plus sum of tangential tooth load and incremental load. That incremental load due to irregularities presented, this incremental load will come to the picture. Then what is the formula used? Dynamic load. That is according to Buckingham equation. The equation number 23.155. Right? So in this FT already we calculated tangential tooth load. The equation 23.87b or 23.93. Any one equation you use, you get FT value. VM also we calculated mean pitch line velocity. Right? What is a B? Phase speed. There is a 10 times of module. Already module we calculated. Just multiply that. Now C is what? Dynamic velocity factor or a coefficient. Right? Am I right? Dynamic load factor, not velocity factor. Sorry, dynamic load factor. This is the unknown. This is only the unknown in this equation. Right? Then how do you calculate dynamic load factor? Then dynamic load factor you can determine is a constant is a kilonewton per meter square or meter newton per meter square. It is by referring table 23.32. Okay, that mainly depends upon the material, pressure angle, and error in action. Again, error in action is represented as F. Again, F you have to determine. Already we know the material, we know the pressure angle. Right? Now we'll again I'll go to the data handbook. This was a dynamic tooth load. The equation number 23.155. 23.155. Yeah. Now see this. The modified dynamic load equation according to the Buckingham's equation, that is Fd is equal to Ft plus, make it correction in the data book also, Ft plus 21 Vm into Ft plus B into C divided by 21 Vm plus square root of Ft plus Bc. Here only unknown is C, capital C. What is C here? C is a velocity factor. See, the C is a velocity factor that depends upon the matching error from the table 23.32. Now where do you get 23.32? That's a page number 23.74. 23.74. Now see that here 23.32. 23.32. The values for C using that equation. Right, 23.115 we use here using that equation. Now the C is mainly depend upon error in action. Again, error in action is unknown. F value is unknown. Again, it depends upon the pinion and gear material and the pressure angle. Based on that, we'll go for take the C value. But see, if you want to calculate C value, error in action is unknown. Then how to determine error in action? That error in action we can determine by using two methods. One is if the class of gear is known, how the gears are cut. It's a precision gear or carefully cut gear. Based on that, we go for calculate error in gear F value. That is by referring the figure 23.34a. Or second one, based on mean pitch line velocity, V is equal to Vm. Again, we go for calculate error in action by referring equation number, so figure number 23.34a. Once you know the error in action, then we go for take the refer the table 23.32. Then you can determine C value. The C value should be in kilonewton per meter square. Now again, I'll move on to the data handbook. How to calculate error in action. That is figure number 23.34a. 23.34. 23.34 34A. It's 23.348. Now I think is visible. Please check. Is a figure number 23.34. In that two figures are there. One is A. That is if a class of gear is known. Now please check is visible. Give me any one answer. Please give me answer.
Yes, sir.
Yeah, for a given module, if module is 5, if the class of gear cut is, it may be precision gear, carefully cut gear, or first class commercial gear. Based on this, if suppose module is 10, for example, if it is a precision gear, it is. Now draw a vertical line here. Into 1 minute. Yeah, from this draw a vertical line here. Then from this draw a horizontal line. Now we'll get the what will be the error F, right? If it is instead of precision cut, carefully cut gear means draw a vertical line up to the model is 10 mm. Draw a vertical line from model 10 mm to the carefully cut gear curve. Then draw a horizontal curve, right? Draw a horizontal line, right? This is the way I have to take the from the figure 23.34a or else 23.35a. What is the 23.35a? Now see the figure number 23.35. Maximum possible error in the gear tooth profile. In that, which one? You go for select A, figure number 8. See the in this it depends upon again mean pitch line velocity. If mean pitch line velocity, for example, it is at 10 meter per second, draw a vertical line that touches the curve, then draw a horizontal line, then take that value. Okay, this is the way you have to take error in action. Okay, any one figure you can refer. Yeah. Now, once you go for dynamic load you calculate, then you go for check whether it is right or wrong. What are the load you calculate? Now, this step I will skip here. This step will not use right now. That completes what? Step number 4. Design against dynamic load. How do you determine design against dynamic load? By referring the equation number 23.155 in this, which is unknown here. C, capital C, dynamic load factor is unknown. How do you calculate dynamic load factor? By referring table number 23.32. In this, error F is unknown. Again, how do you calculate error F? We'll refer 23.34A, the type of uh, class of gear you know that, or else you go for use the mean pitch line velocity. That completes 4 steps. The step number 1, identify the vehicle number. Step number 2, design against static load. Step number 3, take the dimensions of the gear and the pinion. Okay, the dimensions of the gears and pinion. Fourth one, design against dynamic load. And last step, we have design. Last step in this, design against. What is the last load here? Wear load. Wear load occur due to surface destruction of the gear tooth. It may be abrasive wear, corrosive wear, scoring, or pitting. Now, how do you check? I think this slide is visible, or else I'll go for zoom it. Just give me response.
Sir, zoom.
Zoom. Okay. Yeah, now it is visible. Please check. 1 minute.
Yes, sir.
Yeah, now it is visible. Now go for step number 5. Design against wear load. What is the wear load you consider here? Again, refer the data handbook, equation number 23.160. Whatever the wear load is there, D1, BQ, K, that should be greater than the dynamic load. D1 is the physical diameter of pinion. B, the face width, the 10 times of module. Q stands for what? Ratio factor. The ratio factor, I can refer the data handbook. It's a equation number 23.173. It is in the form of either number of teeth or diameter of the gears. This K is nothing but what? Load stress factor. Load stress factor. Now this is a formula used for load stress factor. In this, alpha is the pressure angle, sigma is AC in surface fatigue strength. Again, if the in the problem itself BHN value is given, then you go for use this formula. In the problem BHN value is given, then you go for continue this formula. Load stress factor, then that surface fatigue strength is in terms of hardness number, and then you calculate hardness number is again depends upon the Young's modulus. Okay, then you go for take this. How do you take the Young's modulus? By referring volume number 1. There is a table 2.10 for a given material. These formulas is what's to when BHN value is given for the gear and pinion. If BHN is unknown, means what is the BHN? Brenner hardness number for the pinion and gear is unknown. Then no need to go for this formula. No need to go for this formula. If BHN is unknown. Then from this you go for equating, then you go for determine the K value. Once you determine the K value, then you refer the table number that is not there in the notes. Okay, I'll share it on one more page. Then uh, refer the table 23 point. So please write down this one 23.37b. Once we calculate the K value from the above equation only unknown is K only. Fw is equal to D1 B D1 BQK, that is greater than or equal to FD. FD already we know that. From this you calculate K. Once you calculate K value, then you refer this table 23.37b. Then you go for calculate what? BHN for pinion and gear. This is the method you follow. If BHN is given, then you go follow this method for determine the K. These are the 5 the steps you should follow. And what is the condition here? Whatever the load, the wear load we calculated, that should be greater than the dynamic load. Then only the design is safe. And whatever the dynamic load is less than wear load is less than the endurance limit, endurance load. That is in step number 4. We skip that the procedure. Later, whenever the problem comes, we'll use that formula. Okay. This is the way you have to follow the procedure steps. Right? Remember these 5 steps. What is the 5 step? First, identify the weaker member. First step, identify the weaker member. Second step, design against static load. Then design against. Then third step, determine the dimension. Then fourth step, design against dynamic load. Design against dynamic load. And the fifth step, design against wear load. After that, now these are the some of the note you should remember. So what is the note here? If the design is not satisfied, then you go for change the model, increase the model, and phase width also. Once the model is increases, phase width also automatically increases, because what is the phase width? This times of model. And gear, otherwise you go for change the gear material, or hardness may be improved. BHN value you go for improve. And very important formula is, okay, 10 minutes left. One session is done. Again, please rejoin up to 3 o'clock. I will engage this meeting up to 3 o'clock. What the other formula is here? This is a very important formula. Velocity ratio or speed ratio. It is the ratio of speed of driver to the ratio of speed of driven. The speed and diameters are inversely proportional. Then you know the speed and diameter inversely proportional. That is equal to physical diameter of the driven gear to the physical diameter of the driver. Again, the diameter and number of teeth are directly proportional. The number of teeth on the driven gear divided by number of teeth on the driver gear. This is a formula you should remember. But the other formula is not there in data handbook also it is there. There they consider as the pinion is the driver. In almost all problem, 90% pinion is the driver. In some cases, maybe gear is the driver. That depends upon the given data. Clear? So these are the design procedure you should remember. Next we'll go for solve the problem. It's a 341. Shall I go for solve the problem? Yes, anyone give me response?
No, sir.
And some not audible, please. So wait 1 minute. I'll take that. Yes.
No, sir.
Hmm? You don't want to go for solve the problem? Yes, or else if please familiar with this design procedure, or else we'll go for in next class. We'll solve this problem. Yes, which one is familiar? You decide and tell me. We have another 20 minutes, 17 minutes time. We have. Because if you want to solve this problem, minimum 1.5 hours is required. Yes, shall I go to solve the problem? Better you try. You write the given data. Yes. Let's give me
Sir,
rest.
shall we continue next class, sir?
Okay. Okay. Next class we'll go for solve the problem. Before coming to the next class, be familiar with those 5 steps. Okay. When you go for read the steps, if you have doubts, please call to my number or put a question to my WhatsApp number. Okay. Yes. Thank you. Thank you one and all for attending this meeting. Only 74 members are there out of 102 or 103. Okay, both A and B sections. Okay. Yes, any questions? Yes, next class, before coming to that session, we should have the calculator, then notebook, then pen, pencil, eraser, etc. And data handbook, if you have a soft copy or hard copy, if you have, please get the hard copy of the data handbook also. And also, we should thank your senior, Mr. Tejas. Okay, he has given this the chapter number 23, the Spur uh, the what do you call PDF file. and he used some his juniors or maybe his friends. They made a scan scanner. In the scan scanner, they take the pictures and turn it into PDF and they send to my email ID. Okay, so we should thanks our your seniors here, and also you should, whenever your juniors will ask the help, please help to them.
Yes, sir. Sure.
Yeah, thank you one and all for attending this meeting. Right?
Thank you, sir.
Yeah, we'll see
Yes,
on
sir.
day after tomorrow morning. Okay, first session we have. Okay, thank you one and all. I will end this meeting.